this is a fun thing. I think you will enjoy it. So, single event statistics. Statistics happens in a lot of places. It's a lot of times used by, we've all heard of different websites that, bless you, that we can gamble off of. Like the Gambling Kings or Betting Kings or whatever it's called online. And you're like, oh, I just have to select games and I can win money. The unfortunate thing is how statistics works, especially in the betting world, is usually the person that is setting up the betting situation is creating a favorable outcome for them, not for the bettor. So just please be aware of that. Keep that in mind. We'll go over some things. So probability. Let's see. What that was supposed to do. Oh, that did something good. There you go. Probability, the chance that something will happen, the number of desired outcomes out of the total number of outcomes. So probability is between 0 and 1. Okay? If you turn those into a percent, 0% and 100% is where probabilities will happen. If you're playing a card game, can you have a 160% chance of winning? No. It's not going to happen unless you're cheating, right? You got an ace up your card or up your sleeve or something. So the chance something will happen is probability. The number of desired outcomes on the total number of outcomes. And again, probability is between 0 and 1. Okay? So can we move on, or are we fixed on that? All right. Excuse me. Example number 1. A bowl contains 12 slips of paper. Each has a different name of the month. So January, February, March, April, May, June, July, August, September, October, November, December. Find the probability that if you've shaken it up and you have no idea which piece of paper has what, that you will pull one with the letter J. So best thing to do is you label your outcomes that could take place. So January, February, March, April, May, June, July, August, September, October, November, and December. So how many months are there in the year? 12. Okay, so there are 12 slips of paper because there's 12 months. A bowl contains 12 slips of paper, each with a different name of a month. Find the probability that a slip selected from random from the bowl has the name of the month that starts with the letter J. Is everyone okay with January, June, July? So how many different months have a J starting? 3. How many total outcomes were possible in this adventure? 12. So you have a 3 and 12, which is a 1 and 4 probability that you selected a piece of paper with a J on it. Yeah?
You put A for October.
I don't know. Good thing it didn't affect the outcome, but thank you. Does that make sense? It's pretty basic, straightforward. Number 2 says, suppose you write the names of the days of the week on an identical pieces of paper. Find the probability of picking a piece of paper at random that has the day of the week that starts with the letter T. Well, starting with Sunday, we have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. So there's 7 days in a week, agree? Okay. How many of those happen to start with a T? 2. So I have a 2 in 7 probability of pulling that slip of paper that day of the week starts with the letter T. Okay? Find the probability of picking a piece of paper that has the name ending in the letter Y. It's all 7 of them, isn't it? So you have a 7 out of 7 probability. Okay? Now remember, we'll go back and we said probabilities take place between, they can be 1 and they can be 0 or anything in between. Is 1/4 a number between 0 and 1? Yes. 1/4 is between 0 and 1, right? It's 0.25. What about 2 over 7? Is that between 0 and 1? Yeah. And then what about 7 over 7? That's equal to 1. So that's how that takes place. Again, you can't create probabilities that are higher than 100% or higher than 1 if you don't have it as a percent.
It can be a decimal.
Oh, it definitely can be decimal. Absolutely. I just kept those as fractions because they're simple fractions. That's a great question. And so if it's a decimal, it'd be 0 point, and it wouldn't go above 1 point. It'd be 1.0, nothing higher. All right. Or when we're finding the probability of one event or another, okay, we generally add the probabilities. So think about it. If you had a coin, okay, you have heads and tails on it, right? Now let's just eliminate the probability that we flip a coin and it happens to land right on its edge. Okay? And I know some people are like, dude, it could happen. Have you seen it happen in real life?
No.
No. So we're taking the whole thing that we might flip a coin and it lands right on its edge going, oh, look at that. If it does, take a picture of it. You become an internet sensation. But for the most part, your coin will flip either heads or tails. So if you had heads or tails, or you want to know the probability of some other event taking place, you can generally add them together. Okay? So you roll a standard 6-sided die. We're not calling it dice because dice is plural for die. So a 6-sided die, you have the numbers of 1, 2, 3, 4, 5, and 6, which are denoted by 1, 2, 3, 4, 5, and 6. If those were the die, right? And that's not really important. It's just trying to give you a visual of what it looks like. So you roll a standard 6-sided die. So how many outcomes would be on that die? How many outcomes on just an individual die? 6. I have 6 total outcomes that could take place, okay? So I have 6 outcomes. Now, I want to know what the probability of rolling a 2 or a 5 would be. How many of the outcomes of those 6 are a 2 and a 5? There's 2 of them. Okay? So I have a 2 and 6 probability, which I could reduce to 1 over 3. So 1/3 of the time you roll a die, a 2 or a 6 should come up on the face of the die that you're looking at. Make sense? And then you're waiting for a package to be delivered. The company says there is a 30% probability of arriving Monday, 40% chance it arrives on Tuesday, 20% chance it arrives on Wednesday, and a 10% chance it arrives on Thursday. What is the probability it arrives on Wednesday or Thursday? So we have these. I have 40, 30, 40, 20, and 10. If I add, is 30% 0.3 as a decimal? Is 20% 0.2 as a decimal? Is 40% 0.4 as a decimal? And is 0.1 10% as a decimal? So if I add 0.1 and 0.2, I get 0.3. If I add 0.4, I get 0.7. If I add 0.3 to that, to 0.7, I get 1.0. So here, let me ask you all this. Can you say with confidence that your package will be delivered on Monday, Tuesday, Wednesday, or Thursday? Okay. Why do we know that? Because they told us this is the chance. There's a percent chance that it's going to happen on one of these days. Happens to be that we have, with all those days, that's 100%. Okay, 100% is decimal is 1. Okay, so let's just put it over 100 because we're dealing with percents right now. And let's talk about it as a percent. It says, what is the probability that it arrives on Wednesday or Thursday? Well, what's the chance that it arrives on Wednesday from the word problem? 20%. What's the chance it arrives on Thursday from the word problem? 10%. If I add 10% and 20% together, what do I get? 30%. Okay, I'm leaving these as percents for a moment, but then I could also realize, oh, okay, 30% is 0.3 over 1. Agreed? Now, we don't really like to have a decimal and a fraction mixed together. So what is an equivalent fraction of 0.3 over 1? 3/10. And how you would get that is basically you just multiply this by 10, because if you multiply by 10, it moves the decimal one place to the right. What you do on top of a fraction, you have to do on the bottom, going back to younger years of school. Okay? So, you have a 3 in 10 chance that your package will arrive on a Wednesday or a Thursday. So do you have a better chance that it arrives on a Monday or a Tuesday? May I move on? Everyone following kind of what we're doing? Okay, then you also have probabilities of using not. And not is it's sometimes called the complement of the problem, the event. So if there's a 30% chance that we have a test tomorrow, what's the chance that we don't have a test tomorrow then? 70% chance. Now I'm just making that up. We don't have a test tomorrow, so don't panic. So the complement means you've had the probability of the event, and then you go 1 minus whatever the probability of the event would have been. And that finds you the complement. It's the opposite thinking of it. You know, if someone says, sometimes in medical terms, they might tell you that there's a 95% success rate with a surgery. That means 5% of the surgeries aren't successful. Okay, so there's a chance that, events could, if you look at the complement, sometimes you can flip it. Is it 99? So if this funny question is, well, it's not really funny, but is 99.9% the same as 100%? And a lot of people are, oh yeah, it is. Well, do you understand that on any given day, there's 54,000 airplanes that fly throughout the world? And if you have a 99.9% chance that an airplane makes it to its destination, that means about 212 airplanes crash every day. So is 99.9% the same as 100? Well, talk to those people that are plummeting back down towards the earth going, rah! So it's a much higher rate. So that's kind of the thing to start thinking about. All right, so you roll a standard 6-sided die, so a single cube. So your outcomes are 1, 2, 3, 4, 5, and 6, correct? So let me ask you this. What's the probability that we roll a 6? 1 out of 6. What's the probability we don't roll a 6? How many outcomes are not 6 on this die? 5. So what is the probability that I don't roll a 6? It's 5 out of 6. So do you have a pretty good chance that you won't roll a 6? Yeah, you have 5 out of 6 of your rolls. Now, are there certain streaks of the dice that tend to happen? Like if you ever rolled the die and you get the same number a couple of times? Sure, but if you did an infinite amount of rolls, each side will come up the same amount of times. Okay? And the hard thing is when you look at just a couple of events, you can't make a conclusion off of a couple of events. Okay? That'd be like, you walk down the hallway, you saw 2 people with a cold, and they're, blowing their nose, and they're coughing and sneezing. And then you said, oh, everyone must have a cold then. No, those 2 people could infect a large amount of people by showing up, but they also could build up immunity as well. So, you are waiting for a package to be delivered. The company says there is a 30% probability of Monday, 40% Tuesday, 20% arrives on Wednesday, 10% arrives on Thursday. What is the probability it does not arrive on a Monday? So, what was the chance that it did arrive on a Monday? It was a 30% chance, right? We have a 30% chance. So what would the probability be that it doesn't come on Monday? Yeah, not Monday, but some other day would be a 70% chance. And the reason I know that, if I go 70% and 30%, if I add those together, I get to 100%. 100% is the same as 1.00 as far as the number goes. Okay? So the company says, hey, your package will be there on Monday, or should be there on Monday, 30% chance. Well, if you think of the flip-flop, it's a better chance that it doesn't arrive on a Monday. I mean, it seems good enough, but is a 30% chance really that fantastic? I don't know. I wouldn't sit around all day on Monday going, dude, I can't wait for this package to show up, because there's a better chance, there's 70% chance that it'll arrive on any of the other 3 days that they listed. Okay, and then they did get this. The weatherman says there's a 45% chance of snow tomorrow. So what's the probability that it doesn't snow? 55. So if you have a chance of snow, you can go, well, if I find the complement, if I take the percents, 100% minus 45% is 55%. So you have a 55% chance it doesn't snow tomorrow. You have a 45% chance that it does. And again, you know, my neighbor's Dave Aguilera, the weather guy. He's always wrong. It's awesome. What a great job to have. Oh, well, we're looking at models that do that. Okay, Dave. You're wrong. Is there any part of this that's not making sense at this point? You okay? A little different than algebra, isn't it? Kind of a nice break towards the end of the semester. All right. Now we need to talk about events that is an and. So if I were to be talking about two of you, if I were to say you or you, that's one or the other. But if I say and, that's you and you. It's both of them that you're combining. Okay? So when finding the probability of one event and another event happening, we generally multiply the probabilities. But we need to think about replacement. Okay? So there's two terms that's done in statistics. It's called replacement. Okay? Or replacement or not replacement. So does everybody know what a deck of cards is? There's 52 cards in there if you take the jokers and the rule cards out of it, right? Unless someone's cheating. In that deck of cards, there are 4 kings. Agreed? So if you shuffled your deck of cards and said, okay, what's the probability that I pull a king out? You have a 4 out of 52 chance, which reduces to 1 out of 13, that you pulled a king out of the deck. Now, if someone said, hey, what's the probability that you pull a king, and then your next draw you pull another king, then you have to know, did you put the first king back and reshuffle, or did that first king sit out? If the first king sat out, you no longer have 52 decks or 52 cards in the deck, you'd have 51 because one of them's sitting out. Does that make sense? So let's see if we can go talk about it. This is talking about with replacement. So in this situation, we are putting the card back in. Okay? So they're giving us an event about marbles. A jar contains 100 marbles. Okay? There are 20 red, 20 blue, 30 green, 30 black. So if I go 20 plus 20 plus 30 plus 30, I come up with the 100 marbles. Is that all right so far? Yeah. Find the probability if I pick some marble at random that it is red. Well, how many different or how many marbles are in this jar? 100. And how many of them happen to be red? 20. Okay, can I reduce 20 over 100? Yeah, it becomes 2 over 10. Can I reduce 2 over 10? Yeah, to what? So you have a 1 in 5 probability that if you couldn't see these marbles, like it was either completely sealed container and you're reaching in with your hand and you can't tell the difference by touch, but with the color, if you pull out, this is all shaken up and all mixed together, what's the probability that it's a red would be 1 in 5. So if I pick one marble, look at it, and then pick another, what is the probability they're both red? So again, I forgot to replace it. We replaced it. Okay, so let me see if this makes sense. What if I pick one marble, look at it, replace it, I reshake it up, then pick another marble? What is the probability they're both red? So what do you got?
Yeah, I was about to say something. I didn't read that you replaced it, so I was going to think.
Yeah, that's why I stopped. I had to reread it. So, What's the chance they're both red? Well, we just found out that it's a 1 in 5 chance that we pull a marble out and it happens to be red. Agreed?
Yeah.
Now, I put that marble back in. I shake it back up. Now, let me ask you all this. Does that red marble we just put back in that container that we just shook up, does that red marble know that, oh, you picked me, so I have a less chance of being picked?
No.
No, marble doesn't have memory. Okay? So, what's the probability that I pick another red marble out? 1 out of 5, 20 out of 100. You're right. Okay? Now let's multiply these events together. Multiply them. 1 times 1 is 1. Good? 5 times 5 is 25. So let me ask you all this. Do you have, if your friend came up with a game and said, hey, if you pull a red marble out of the jar, I'll buy you lunch. Or if you have 2 turns, if you pull a red marble out of the jar, you have to buy me lunch. That's a pretty safe bet because 1 out of every 5 times on a single event, the red marble's chosen. If you did the event twice, you have a 1 in 25 chance that'll happen. What's the chance that you don't pull a red marble and a red marble, or 2 different red marbles, or 2 red marbles out of this jar? If it's 1 out of 25 you do, it's got to be 24 out of 25 that you don't. So do you have a better chance of pulling some other combinations of marbles out than a red and a red? Now, could the first one be red and the second one be a different color? Yeah. Could the first one be a different color and the second one be red? So those are all outcomes that we have to deal with. Okay? Now, next part, C says, if I pick one marble, look at it, replace it, and then pick another, what is the probability that neither are blue? Okay? How many blue marbles are there? 20. So that's 20 out of 100, which reduces to 1 out of 5. So if not picking blue, not blue, is 4 out of 5. Okay? Then pick another one that neither. So you have a 4 out of 5 chance that the first choice wasn't blue. You put the marble back in, you shake it back up, and you have a 4 out of 5 chance that you pick the other. So that's 16 out of 25 chances that neither of your marbles are blue. If I pick one marble, look at it, replace it, and then pick another, what is the probability we get at least one green one? At least one green one. So your pick could be green, could be green other color, it could be other color and green. So this will be the last part I'm going to give you. Yeah, I'm salty. Okay, if I pick one marble, look at it, replace it, then pick another marble, what is the probability that I get at least one green marble? How many green marbles are in our jar? 30. So 30 out of 100 reduces to 3 out of 7. Agree? And then, so the probability that I pick a second one is 3 out of 7, which that is 9 out of 49. So that's both green, right? And then I have to think about this. I could do a 3 out of 7 times a 4 out of 7. Okay? So that's going to give me 12 out of 49. And so that means one green and one not. Okay? So my choices are, they're both green, or one's green and one's not. So if I add this event, 9 out of 49, to this event, 12 out of 49, how many outcomes could take place? What's 9 plus 12? 21. And then 49, just keep that. So you have a 21 out of 49 chance, which will reduce to a 3 out of 7 chance, because 3 goes in both, that at least one. I didn't get to the last slide, and we'll get to that tomorrow. But I want to have you guys and girls start this. It's 1 page. It's just a front. Huh? Right.
We're doing this for homework?
Yeah, get a good start on it. Have a great day, everybody. Oh, you got pins on your desk.
That's right. That's right. You guys are working on the. How's it going?
Started okay.
That's Johanna and Bill that go to that stuff. I'm working on the geometry.
Are you?
Yeah.